Howdy! The topic for today is inverse trigonometric functions. Inverse trigonometric functions are the last kind of transcendental function that we will be talking about. Our main goal is just developing the derivative formulas for these inverse trigonometric functions. And we're going to discover that the derivatives of these functions are connected to algebraic functions in a really nice way that is going to be especially useful later when you talk about integration. As we dig a little deeper, thinking about the connection between functions and their inverses, we're going to find that there's a fundamental relationship between the derivative of a function and the derivative of its inverse. And that relationship can be exploited to calculate the derivatives of new kinds of functions, as we'll see.
Hello, calculus students. Today's topic is derivatives of inverse trigonometric functions. Let's start by reviewing inverse trig functions, and we'll start with the inverse sine function, which is sometimes called arcsine, and we'll, in parallel, do the inverse cosine function, or arccos. We'll begin by looking at reminding ourselves what the graphs of these two trig functions look like. On the left there, you got the graph of the sine function, and on the right, you got the graph of the cosine function. Now, I just want to point out that neither one of these functions is one-to-one. They both fail the horizontal line test, right? If I draw a horizontal line, it crosses through these graphs multiple times. So these functions are not one-to-one on their natural domains of negative infinity to positive infinity. And that's problematic because, if they're not one-to-one, then they don't have inverses. But here we are, we're wanting to talk about the inverses of these functions. So the way that we get around a function that's not being one-to-one on its domain is we take a smaller subset of its domain. In other words, we restrict the domain. And on the sine function, if I would restrict its domain to negative pi over 2 to positive pi over 2, it would be one-to-one there. So if I just look at this piece of the sine function, it goes from here to here, it does actually pass the vertical line test there, right? I'm not vertical line test. It does pass the horizontal line test there because the green part of the graph is only crossed by a horizontal line once. And similarly with the cosine function, if we restrict its domain to be between 0 and pi, it passes the horizontal line test there. So those are the restrictions we're making on the domain just to get something that's one-to-one. Looking at the graph, after we've restricted it to the green part, we would say the domain of sine here is negative pi over 2 to positive pi over 2. And then the corresponding range is negative 1 to positive 1. Anytime I'm going to think about inverse functions, I have to think about what the domain and range of the original function is. Likewise, when we're dealing with the cosine function here, we're making the restriction of 0 to pi for its domain, and then its range will be negative 1 to positive 1. Those are the y values on the graph. So now, because we have a function that's one-to-one on its restricted domain, we know that an inverse exists for both of these. We got a sine inverse exists and a cosine inverse exists. And you may remember from a previous lesson that what the inverse function does is it switches the domain and range of the original function because, remember, it just switches the x's and y's, right? So the domain of sine inverse is just going to be the same as the range of the original sine function, which was negative 1 to positive 1. So this inverse sine function is going to allow inputs between negative 1 and positive 1. And the same thing happens with the inverse cosine function. The domain of cosine inverse is the same as range of cos, which is negative 1 to positive 1. And the range of sine inverse is the same as the domain of sine, which we've restricted to negative pi over 2 to positive pi over 2. And for cosine, the range of cosine inverse is the domain of cosine, which was restricted 0 to pi. Now we know for our inverse functions, we know what their domain and range are. And that's important. We have to know when we're dealing with some new function, especially strange ones like this, what numbers are we allowed to plug into it? What kind of numbers will we get as outputs? In other words, what's the range? And one little bit of information here that's vital is that anytime you write an equation of the form y equals sine inverse of x, we can convert that to an equivalent form, x equals sine of y. Because remember, all that the inverse function does is just interchange the role of x and y, right? And similarly, we can write x equals cosine of y is equivalent to y equals cosine inverse of x. To get a little bit of a feel for this last thing that we wrote in terms of specific values, on the left there I could ask, what is the sine inverse of 1/2? Well, I have to think about that in reverse. I have to say, what angle between negative pi over 2 and positive pi over 2 has a sine value of 1/2? And the answer is pi over 6. Pi over 6 is that unique angle in the correct range there that has a sine of 1/2, because sine of pi over 6 is equal to 1/2. And similarly with the cosine over there, I could say, what's cosine inverse of square root of 3 over 2? So I have to think, okay, what angle between 0 and pi, because I got to use that for my range, right? What angle between 0 and pi do you plug into cosine and you get square root of 3 over 2? Well, it turns out that that would also be pi over 6. Because when you plug pi over 6 into cosine, you get square root of 3 over 2. So you see what's happening, just the x's and the y's are getting switched, right? And you just got to be careful about what interval you're allowing your inputs to be in and what interval the outputs have to come in. And we can run through exactly the same sort of thing for the other 4 trig functions too. So this covers sine and cosine, and it all came down to looking at the graph of the function and restricting it appropriately so that you have something that's 1-to-1, so that you'll have an inverse. So we could do that simultaneously for tangent inverse and for cotangent inverse. So for tangent inverse, I got to find a piece of that function where it's 1-to-1. I see lots of pieces where it is 1-to-1, but the sort of standard answer is to pick this piece right here. So tangent is 1-to-1 if you restrict your attention to that little piece of the tangent function. And similarly, the cotangent function, we usually pick this piece right here between 0 and pi. So since we're picking a piece to restrict the function to, that's going to be our restriction to make it 1-to-1. So here toward the bottom, I was just saying, hey, both of these functions, they're not 1-to-1 on their natural domains, which include all the real numbers except for where they have those asymptotes. And so for our tangent, it would be 1-to-1 if we restricted that one to negative pi over 2 to positive pi over 2. And the cotangent is 1-to-1 if we restrict it between 0 and pi. And so with that restriction in place, what's our domain and range looking at the graph up there? Well, we're saying we want the domain to be negative pi over 2 to positive pi over 2. Endpoints not included, because those are where you have asymptotes. And if you look at that green piece of the curve up there on tangent, what's the range of it? Well, you see that you get all real numbers as output values. So that would just be all of r. Or if you want to put the interval negative infinity to positive infinity, that'd be okay too. And then for the cotangent, we restricted the domain to the interval 0 to pi. Again, endpoints not included because that's where you have asymptotes. And then the range would also be the set of real numbers on this one, because you can see that the y values on that graph up there extend from negative infinity to positive infinity. So now that we got our functions suitably restricted so that they're 1-to-1, then we can get into talking about the inverses. So inverses exist, and we know that the domain of the tangent inverse function is just going to be the range of the original tangent, and the range of the tangent inverse is going to be the domain of the original tangent. Same thing for cotangent inverse. It interchanges the domain and range compared to the original function. So the cotangent inverse function and the inverse tangent function, you can plug any number in the world you want to into them, but the output values are going to be restricted to be in those intervals. For tangent inverse, you only get outputs between negative pi over 2 and positive pi over 2, and for cotangent, you only get outputs between 0 and pi. And then we have the equivalent way of writing the equation y equals tangent inverse of x. In terms of the original function, that equation is equivalent to x equals tangent of y, and y equals cotangent inverse of x is equivalent to saying x equals cotangent of y. That's sort of our conversion factor. Anytime we're trying to answer something about the inverse function, we can convert it back to a question about the original function, which is kind of nice. And then as a specific example there at the bottom, I can say, hey, what is tangent inverse of 1? Tangent inverse of 1 just means what angle do you plug into the original tangent between negative pi over 2 and positive pi over 2, because that was the restriction on our domain originally. So what angle between negative pi over 2 and positive pi over 2 do you plug into tangent and you get back 1? Well, I know that tangent of pi over 4 equals 1, and pi over 4 is in the appropriate range. And the reason this is true is because tangent of pi over 4 equals 1. On the right, I've got an example there with the cotangent inverse of square root of 3. How would you figure that out? Well, let me do a little scratch work down here. Cotangent, just being a little informal here, is cosine over sine. And I know that sometimes I get square root of 3 out of sines and cosines, like so. So if I can find an angle in the appropriate interval where cosine is square root of 3 over 2 and sine is 1/2, then I would have my angle. Well, I know that cosine is equal to square root of 3 over 2 at the angle pi over 6. So pi over 6 is going to be your answer here, because pi over 6 is between 0 and pi. That's where it needs to be. And then we have secant and cosecant to do next. So there's a quick reminder of what the graphs of secant and cosecant look like. So those aren't the graphs of the inverse functions. Those are the graphs of the original secant and cosecant functions. And those are just the reciprocals of the cosine and sine functions, right? That's why you have asymptotes, is because when you reciprocate the cosine function, all the places where the cosine function crosses the x-axis, you get 0 in the denominator when you reciprocate that. So yeah, you get a lot of asymptotes. These things are not one-to-one, and so we need to make some restrictions to make them one-to-one. And then on the secant graph, the restriction to make is you go like from here up this side of the asymptote, and then here down this side of the asymptote. So you restrict the secant function between 0 and pi, not allowing pi over 2 because of the asymptote. And then on the cosecant, you restrict it like this. And restricting there, you get something that is one-to-one and gives you all the possible output values of the original function. So we're making the restriction 0 to pi over 2, pi over 2 not included, then union with pi over 2 to pi. So that just leaves it just jumps over that asymptote there. And then we do the similar sort of thing with the cosecant function to make that restriction. The whole point of making that restriction is just to get the one-to-one functions, and then summarizing what their domain and ranges are here. All right, so now upon making this suitable restriction, we know that our secant inverse and our cosecant inverse functions exist, and we get their domains just by interchanging domain and range with respect to the original function. So the domain of your secant inverse is negative infinity to negative 1, union positive 1 to positive infinity, and its range is 0 to pi over 2, union pi over 2 to pi, where you have pi over 2 excluded there. And similarly over here with the cosecant inverse. Okay, I know all this seems a bit technical, but we still have that one equivalence. Anytime you would say y equals secant inverse of x, that's equivalent to saying x equals secant of y. And if you would say y equals cosecant inverse of x, an equivalent way to write that is x equals cosecant of y. Now that we understand our inverse functions a little bit better, it makes sense to start thinking about what their derivatives are. So let's calculate the derivative of the sine inverse function. So we're going to start by, letting y equals sine inverse of x, and what we want to do is find dy dx. At this point, the only thing I could think of to do that's kind of naive would be to just maybe use the definition of derivative. But you could try it, and we just don't have enough good things that we know about the inverse sine function to make that work. But what we can do instead is use that conversion factor that I was talking about. If you have y is equal to sine inverse of x, we can write that equation can be encoded a different way, an equivalent way. by writing it as x equals sine of y. That converts it, the equation, into something we know something about. Like, we know what the derivative of sine is. So the idea here is to take this new equation and implicitly differentiate with respect to x. So we'll take derivative with respect to x of both sides of this equation, x equals sine of y. On the left-hand side of that equation, you just get 1. On the right-hand side, you're differentiating something that has a y in it. So derivative of sine of y would be cosine of y, but then you have to multiply times y prime according to the chain rule. So then you can take that equation and you can solve for y, and you'd get y prime equals 1 over cosine of y. In other words, dy dx equals 1 over cosine of y. Well, that's all well and good, and we're close to an answer, but the problem is the original function, y equals sine inverse of x, was given in terms of the variable x, and our derivative formula that we have right now is in terms of y. So what we need to do is convert that back into the variable x. And to do that, we need to think about a picture, or we need to think about identities. There's a few ways you can go about it. I can give you the algebraic, let me give you the algebraic way of doing it. You can also think about it geometrically. But we know that sine squared of y plus cosine squared of y equals 1. And then we know from there, cosine squared of y is equal to 1 minus sine squared of y. And then we could solve for, like, take the square root of both sides to get cosine of y by itself. So cosine of y would be plus or minus the square root of 1 minus sine squared of y. Now I want to remind you of something. What's another name for sine of y? Well, if you look back at what we did earlier, sine of y can be expressed as x. So this becomes cosine of y equals plus or minus the square root of 1 minus x squared on account of x being equal to sine of y. And now there's just one last little issue we need to think about. We got to think about the sign of this in front. We got a plus and minus in front of this radical. I want to know whether it should be plus or whether it should be minus. We know that when we're thinking about inverse functions, there's restrictions on the domains, right? For sine inverse to make sense, for y equals sine inverse of x to make sense, we restrict y. Let's see, for the sine inverse function, we got a restricted range of negative pi over 2 to positive pi over 2. But cosine of y is greater than or equal to 0 whenever y is between negative pi over 2 and positive pi over 2. Cosine's positive because you're talking about the second or the first and the fourth quadrants, and if you think about any angle over there, the x values are positive, so that means the cosine's positive. So cosine's positive, so that means that we go with the positive radical here. Cosine of y has to be positive square root of 1 minus x squared. Anyway, the moral of the story here is that that's what cosine of y is equal to in this derivative that we were calculating a minute ago. Cosine of y is equal to positive square root of 1 minus x squared. So our dy dx that we were wanting to find magically turns out to be, well, not magically. I showed you, I guess, all the reasons why. But maybe somewhat surprisingly, turns out to be this expression involving radicals. So there's a formula for derivative of, just to be clear here what we actually calculated. So what we showed was that the derivative with respect to x of sine inverse of x equals 1 over square root of 1 minus x squared. Now I realize that may be a little bit to take in, but if you study it and go through it carefully, it's comprehensible. It just involves understanding how trig functions work, how they relate to their inverse functions, and then using the Pythagorean identity and understanding, where trig functions are positive and negative. But yeah, I mean, this sort of thing is not going to be on the test, but I do want you to see at least once, like, how you come up with one of these derivative formulas. Now, the thing is, I could do a very similar sort of calculation to get the derivative of cosine inverse, for tangent inverse, for secant inverse, for cosecant inverse. And I'm not going to do all of those, of course. I just wanted to show you how one of them worked. And so here's a summary of what all the derivatives turn out to be. So here's the one we just computed in the top left. And then the table's arranged nicely here because notice on this first row, when you compare the derivative of the sine inverse to the derivative of the cosine inverse, look how similar their formulas are. The only difference is the sign right there. And similarly, when you look at the second row, when you look at the derivative of inverse tangent and inverse cotangent, they're the same except for the sign there, right? So this is nice. It means you don't really have to remember so much. You just have to remember which one gets the positive and which one gets the negative. And then lastly, you've got the secant inverse. This one strangely has an absolute value in it, as well as the cosecant inverse. That absolute value arises from thinking about cases where things are positive and negative, like certain trig functions are positive and negative. It just comes out in the wash. But yeah, so those are your derivative formulas that you need to know for inverse trig functions. So these are just formulas that need to be committed to memory. And luckily, these are the last of the sort of basic differentiation formulas that you need to know. That's the last of them. So the amount of stuff that you have to commit to memory is really not too great. You've got your general rules, like, the power rule, the quotient rule, the product rule. And you've got a few general procedures like implicit differentiation and logarithmic differentiation. And then you've got a few specific derivative formulas that you need to know, like the derivative of e to the x, the derivative of natural log, the derivative of b to the x, and the derivative of log base b. And now you've got these derivatives of inverse trig functions. And that's everything. So, not so bad. Let's put these to use to calculate some derivatives. In this first example, dy dx for y equals sine inverse of e to the negative 2x is the typical example where we have one function inside of another and we have to use the chain rule. So we differentiate the outside function, which is sine inverse, and we see its formula up there, so it'd be 1 over the square root of 1 minus whatever's on the inside of the sine inverse function squared. So this would be e to the negative 2x, then you got to square it. Then you got to multiply times the derivative of the inside function, and the derivative of the inside function would be negative 2 e to the negative 2x. And doing some minor simplification here, we'd get okay. And then on the second example, we're taking a natural log of a tangent inverse of 1 plus 3x. So this would be an example where we need to use the chain rule a few times. Well, the derivative of the outside function, the natural log, you just do 1 over whatever's on the inside. But then you got to take the derivative of what's on the inside. And so now we got to do that next derivative. Okay, so our formula for differentiating the tangent inverse, it's 1 over 1 plus whatever's on the inside squared. So you're going to have 1 over 1 plus the inside stuff squared. And then lastly, you have to take the derivative of the inside stuff again. So that'd be 1 plus 3x prime. But that derivative is really simple. That's just 3, right? So I'm just going to go ahead and put 3 here. And that's it. And for this last example, I'd like to calculate dw dx. Okay, dw dx. To take that derivative, I will use the product rule because it's a product of 2 to the x times this cosecant inverse. Well, let's see how that'll go. So you take the derivative of the first thing. Derivative of 2 to the x is natural log of 2 multiplied times 2 to the x. Then I'm going to leave that cosecant inverse of cosine x squared alone plus Then I'm going to leave the 2 to the x alone. And now I'm going to take the derivative of the cosecant inverse. Well, let me remind myself what the derivative formula for cosecant inverse is. That's this one here. So I got to do a negative, and then 1 over, and then I got to have an absolute value of whatever the inside is, and then square root of the inside squared minus 1. So it'll look like times negative 1 over absolute value cosine x squared times the square root. Then I got to do whatever was in the inside of the cosecant function squared. So that'd be cosine squared of x squared minus 1. Then I have to multiply times the derivative of cosine of x squared because our cosecant inverse function had an inside function itself, so we have to multiply times the derivative of that. Rather than having to copy everything down again, let me just go down here and say, well, cosine of x squared prime is equal to, well, you differentiate that outside function, you get negative sine of x squared, and then you got to multiply that times 2x, which is the derivative of its inside function. So I'm just going to put that in right here. So it'll be times negative sine of x squared times 2x. So there's that derivative. A little bit yucky, but that's the way it goes. I think, though, the moral of the story here is that you've got a set of derivative formulas that you just, you have to start practicing using them and getting them sort of memorized. But, the way you use them is just like using any other derivative formula. You just quote the formula, and if there's some function on the inside, like in this first example, there was an inside function, e to the 2x. E to the negative 2x, you just put in place of x when you do the formula, and then you just got to use the chain rule in addition. All right. We can do an application here using our knowledge of how to take derivatives. So we could find the equation of a line tangent to the graph of y equals sine inverse of x over 4 at the point where x equals 2. Since we're talking about the graph of this function at this point where x is equal to 2, it might be nice just to have a little bit of a visual on that. So let's go to Desmos and graph that and see what it looks like. Okay, so here's the graph of y equals sine inverse of x over 4. And then the red point is the point where x is equal to 2. So you can see the coordinates there are 2 comma pi over 6. Because if you plug 2 in for x, you're doing sine inverse of 1/2. And sine inverse of 1/2 says, at what angle is the sine function equal to 1/2? And the answer is pi over 6. We want to find the equation of the tangent line at that point, so we need to know the slope of the tangent line. So m tan is going to be the derivative of y with respect to x at the value x equals 2. So first let's find dy dx. Well, dy dx, if I use my formula for the derivative of sine inverse, I come up with 1 over the square root of 1 minus whatever's inside that sine inverse function squared. So that'd be x squared over 16. Then I got to multiply times the derivative of the inside function, which is 1/4. So this is 1 over 4 times the square root of 1 minus x squared over 16. And so now I can plug in x equals 2. So dy dx when x is equal to 2 is 1 over 4 square root 1 minus, well, if I put 2 in there, I'm going to get 1/4. So that's 3/4 inside the radical. So this is 1 over 4 times the square root of 3/4. I can take the square root of that 4 in the denominator, and I'd get a 2 in the denominator there, and it would cancel with the 4 out front, so I'd get 1 over 2 square root of 3. Okay, that's fine. So that's my m tan. And then my point is there. So the equation of the tangent line is going to be y minus the y coordinate equals the slope of the tangent, 1 over 2 square root of 3 times x minus the x coordinate on that point. And that's the answer we're looking for. It turns out that there's a there's a general theorem that tells you how to calculate derivatives of any old inverse function. Could be an inverse trig function, could be whatever. If you have a function and you know it has an inverse, then this is a pretty cool theorem. It tells you how to calculate the derivative of the inverse function without even knowing what the formula for the inverse function is. Of course, there are some hypotheses that says your original function f has to be differentiable and it has to have an inverse on that some interval I. And then this x naught here is just some point in that interval where the derivative is not equal to 0 of the original function. If all that happens, then the inverse is going to be differentiable at y naught equals the f of x naught, and then you have this formula right here for what the derivative would be. The derivative of the inverse at y naught is just the reciprocal of the derivative of the original function at x naught. And y is equal to f of x naught there. So graphically, what this is saying is, in red here you have the original function, y equals f of x, and then I've drawn a little tangent line there to sort of give you a visual for what the derivative is at that point. The derivative is the slope of that line. So remember that whenever you graph an original function and then you graph the inverse, you get the inverse just by taking every point that's on the original graph and reversing the coordinates. So x naught y naught becomes y naught x naught when you graph the inverse. So if you think about it, because slope is change in y over change in x, well, the change in y over change in x at that point on the red curve, when you think about the corresponding slope on the blue curve, well, change in y over change in x gets reciprocated because of how the inverse function is formed just by reversing x and y. So instead of having change in y over change in x, you have change in x over change in y. So it's just reciprocating the slope. Another way to look at this formula, another way to sort of put it into notation, so if you have y is equal to f of x, we know that that's equivalent to saying x equals f inverse of y. This one on the right here, you know something about. You know how to differentiate it. And then you want to know how to differentiate this one. So the way that works is you can calculate the derivative of x, that's the inverse function, with respect to y by doing 1 over dy dx. Just like the way real fractions work. Kind of like you could say, whatever, 1/2 is the same as 1 over 2 over 1. Something like that. This formulation of it over here is useful if I want to calculate the derivative of the inverse function using my knowledge of the original function. Let me give you a couple of examples to sort of make you feel a little bit more familiar with this derivative of an inverse function theorem. In this example, we've got the function f of x equals natural log of 5 times x plus e, and we're looking at this specific point on the graph of that original function f. So that's telling me that my x naught is 0 and my y naught is equal to 1, making reference to the original theorem. So the x naught's the point you plug into the derivative of the original function, and y naught is the point you plug into the derivative of the inverse function. And I want to find this derivative of the inverse evaluated at y naught equals 1. So that formula up there said that if I want that derivative, the derivative of f inverse at 1, it's 1 over the derivative of the original function, but evaluated not at 1, evaluated at 0, which was the x value of the point on the graph. Well, we should be able to do this because over here on the side, we know f of x is equal to natural log of 5x plus e. So its derivative, f prime of x, is 1 over 5x plus e. But then multiply times the derivative of the inside function, which is 5. So I'm just going to write that as 5 in the numerator there. But I need to know what f prime of 0 is. Well, that just means put 0 in for x. So I'd get 5 over 5 times 0 plus e, so 5 over e. So then going back to my problem I was working on, the derivative of f inverse at 1 is 1 over f prime of 0, which we just discovered is 1 over 5 over e, which I'll write as e divided by 5. So we got that derivative without even having a formula for the function we just differentiated. So that's kind of cool. So here's the function, f of x equals x to the 2/3. And I want to find the derivative of that function's inverse. And I want to do it without even knowing what the formula for the inverse function is. It's slightly magical, it seems. Calculating derivatives of things that you don't even know the formula of. Well, you can do it. So we can say, well, just like let y equal x to the 2/3, right? F inverse prime of y means the same thing as doing dx dy. Well, to do dx dy, you do 1 over dy dx. Well, see, I know what dy dx is just by looking at this formula right here, y equals x to the 2/3, so I can compute it. And what do I get for dy dx? Well, dy dx would be bring the 2/3 down, then you get x instead of the negative 1/3, right? Or if you want, you can write that as 3/2 x to the positive 1/3. But you got to be careful here. You might think that you're done, but notice that our original variable was y, and now we've got it converted to an x. I want to get things back to in terms of y. Just a little algebra over here on the side. If y is equal to x to the 2/3, then what is x to the 1/3 equal to in terms of y? Well, you're taking the square root, it looks like. If you take the square root of y, you get x to the 1/3, right? So what I have here is really 3/2 times the square root of y. So now the variable matches what I started with at the beginning and what I have at the end. And so if I want to put things back in terms of the variable x, I can just say f inverse prime of x is equal to 3/2 square root of x. Now, if you don't believe me, you can check. Because if y, in this particular example, I could find the inverse. I could find the inverse first before I calculate the derivative of it. So to get the inverse, I could just, solve for x in terms of y, and you'd get x is equal to y to the 3/2. And then what do you get when you do the derivative of x with respect to y? You get 3/2, bring the 3/2 down, and then y to the 1/2, right? And so it matches like here and here. Now usually though, this middle step here where I solve for x in terms of y is the tricky part. Like you can't always do that. So I can't always check my answer like this. So that's what's cool about this general theorem about how the derivative of the inverse function can be had from the derivative of the original function, because you don't necessarily have to know what the inverse function is in order to find its derivative. Okay. In fact, I could verify that our derivative formula for the cosine inverse function. We already know what the answer is. It was one of the ones I gave you in that table of derivatives a little while ago. We know that the derivative is 1 over, there's a negative 1 over square root of 1 minus x squared. I already know that's the answer, but I want to show you how what we just did can be used to get that answer. So if y is equal to cosine of x, then we know that x is cosine inverse of y. If I take the derivative with respect to y of cosine inverse of y, notice that's really just doing the same thing as the original here. That's dx dy. So I can write that as 1 over dy dx. And y is cosine of x, so this is 1 over the derivative of cosine of x is negative sine of x. So I get 1 over negative sine x. But again, I've got this issue where the variables are mismatched. I've got a y here, but I've got an x here. So I have to convert the variable back to y. The way you can do this is because x is between 0 and pi but x is between 0 and pi, I can think of that as an angle of a triangle. And it won't matter whether it's in the first quadrant or the second quadrant. And I know that cosine of this angle x is equal to y from the very beginning. But cosine is, I can think of that as y over 1, but I can also think of cosine as the adjacent over the hypotenuse of this right triangle with the acute angle x. And so I can label the adjacent side of this triangle y and the hypotenuse 1. And then the vertical side is got to be a positive, well, let me just call it a for a moment. I know a squared plus y squared equals 1, so I can solve for a squared, get 1 minus y squared. So a is plus or minus the square root of 1 minus y squared. But because that angle x is in the first or the second quadrant, that vertical side of the triangle is going to be pointing upward, so this a is always going to come out positive. Now I can read off from that triangle, what is sine of x? Well, from that triangle, sine of x is the opposite over the hypotenuse, and that just works out to be a, which is square root of 1 minus y squared, over 1. And so you end up with 1 over negative the square root of 1 minus y squared. And now my variable matches what I started with. And so now I can put the variable back to x if I want to and just say derivative with respect to x of cosine inverse of x is equal to 1 over negative square root of 1 minus x squared, which was the formula that we were expecting. So that's kind of cool. But the main thrust of what that theorem is about is it tells you how to get the derivative of the inverse function using only knowledge of the original function's derivative. Okay, so that's a lot to think about for one day. It's okay if you got to go back and rewatch parts of things and also try to work through some details on your own paper and then reference the textbook. And if after all that you're still feeling a little confused, it's always a good idea to come ask questions. So I'll leave it there and tell you goodbye. See you later.